Okay, so
Can't hear you.
Professor Bhatia, can you now?
Yeah, okay. So I'm happy to welcome everybody to the first talk of this semester. We are meeting after some break. And I'm very happy to welcome Professor C.S. Rajan, whom I have known for more than 35 years. A very well-known mathematician, has spent all his career at the PIFR. And I'm happy to tell you, he'll be joining Ashoka from the next semester. So it's appropriate that our first talk is being given by him. He is an expert on representations of Lie groups and topological groups, elliptic surfaces, number theory, automorphic forms, etc. And we requested him to give a talk accessible to our undergraduate students, to which he kindly agreed. Welcome, Rajan.
Oh, thank you, Bhatia. It's been thanks to all of you, to you and Krishna and to Gaurav for arranging this talk. It is a great pleasure, and looking forward to being at Ashoka. So let me start. Just a minute. So yeah. So the theorem of Pythagoras or Pythagoras, whatever it is, was known to most ancient civilizations, Babylonians, Indians, Chinese, and it occurs in the Sutras, which are some couple of centuries or some such things before the advent of Pythagoras. Okay, so what is a theorem? Just a minute, let me, I think I have to, this slide windows, how do I want to remove this. Okay. No, it's not. Okay. Let me just. Yeah, so from the Baudhayana Sulta Sutra before Pythagoras, this is not a couple of centuries, it's the dates are possibly between 1000 to 800 BC. So the theorem is that that's a statement which has been translated to English. A rope stretched along the length of the diagonal produces an area which the vertical and horizontal sides make together. So you're taking the diagonal of a right angle triangle, and so what it says is the standard theorem which all of us know from school days. So I just want to say what is an artistic impression of a picture of Baudhayana. So this, of course, nobody knows. This is supposed to be a bust of Pythagoras in marble. So this again, it's not clear that Pythagoras, this is actual reality or some image of the artist. So what is the theorem? The Pythagoras theorem. So we have a right angle triangle. That means the base which has length A and the height which is length B, and so there is a right angle. It forms a right angle, and the hypotenuse is called has length C, and the square of C is equal to A squared plus B squared. Yeah. So that's a theorem of Pythagoras. So if A and B are the lengths of the two sides containing the right angle, and C is the length of the hypotenuse, then Pythagoras theorem is a statement that C squared is equal to A squared plus B squared. Okay, so that everybody knows. So I just want to say a bit of, take a digression. So this is a story of Enrico Castelnovo. He was a 19th century Italian writer. He was known for his role in the unification of Italy. And he writes about his school days when he had to face an exam on the final exam. He wrote a short story titled The Theorem of Pythagoras, where he recounts the story of his failing the school exam, unable to give a proof of this theorem. And because of that, he could not give a proof of this theorem. He had to discontinue his education. So his examiner's comments when he failed was this. This was an oral exam. And he says, "Is that all you have to say? Don't you know even know that this theorem of Pythagoras is known as donkey's bridge because only donkeys cannot cross this bridge. I suppose you know that you have not passed this examination. You should know the price you have to pay for reading Don Quixote or drawing pictures of cats during my lessons. So that is a state of education in Italy 150 years back, where you don't do some basic mathematics, then you drop out of college education. And this is a picture of his son, Guido Castelnovo. He is a celebrated Italian algebraic geometer. And 27 years later, the father quizzes his son. When he sees his son doing this Pythagoras theorem, he quizzes him, tries to see whether he knows it or not. And he gets a reply from the son. As you very well know, all except absolute donkeys understand the theorem of Pythagoras. The same words came to haunt him 27 years later, but this time from his son. As I said, that was the state of education in late 19th century Italy. Of course, Guido Castelnovo, maybe because of his father's experience with education, later on did a lot about mathematical education, has this to say about mathematics education. Yeah, it is often preferable to proceed by successive approximations. Wait, just a minute. Where each step is evaluated in relation to actual facts in order to separate true from false bit by bit, rather than to rely on impeccable logic cut off from the exterior world. Okay, he goes on to add, the emphasis on demonstrating through logic undermines reasoning, which has a different function, and intuition by not acknowledging its immense value. Okay, if we strip elementary geometry of a whole series of mental gymnastics which serve no purpose, we will be able to make mathematics enjoyable to everyone and at the same time nurtures several mental faculties. So that is Guido Castelnovo. Anyway, so that's a bit of a digression, hoping to warm up to the subject. And this source is Bhavna, January 2018. The translation is by my good friend and colleague C.S. Aravinda. So it's a good journal to see. So now let's go on to a proof of the Pythagoras theorem from the Sulta Sutras, which is far easier than the proof which Enrico Castelnovo had to struggle with. So what is the proof? The proof is, there's a famous picture. And this was the proof which was there in my school textbook, but I did not understand it at that time, the significance of it. But so here is it. So we are taking a right triangle, which is ABC. And so we form four right triangles, we put it to the corner. And what we know is that the sum of the angles of a right triangle is 180 degrees. So the two complementary angles away from the right angle add up to 90 degrees. So as a result, when you do this angle is 90 degrees. This angle plus this angle is 90. And this is a square. So you can add the square. So this also is 90 degrees. So what happens is you actually get a straight line. This is a straight line. This is a straight line. This is a straight line. So you get a square of size A plus B. And inside you have four triangles. And that is another big square, which is C. So now you just count areas. So what you get is that the entire area outside is A plus B whole square, which is A squared plus B squared plus 4AB. But you are having this four squares out here, which is 4 into half of AB, which is 2AB. So when you, A squared plus A plus B whole squared is A squared plus B squared plus 2AB. So what you get is, so here is a proof. So sum of the angles of a triangle is 180 degrees. If two lines meet at an angle of 180 degrees, then together they form a straight line. Right? Combined together, this says that the figure formed in the previous slide is one square of side C contained in a square of side A plus B. So now we just expand A plus B whole square is C squared plus 4 times the area of this triangle, which is AB by 2, because it's half the area of the rectangle. And you get thus it's equal to A squared plus B squared equal to C squared. So that is a proof which was given in the Sulta Sutras. It is far better than the proofs which are in Italy 150 years back. It's really one of the great proofs. So this pictorial proof of Baudiana has been adopted as the official emblem of the ICTS and branch of TIFR at Bangalore. Bhaskara, which is centuries later, upon seeing the proof, is said to have remarked, this is it, meaning that it is the proof. There is some beauty and elegance to the proof, and he just saw the proof and said, this is supposed to be it. This is really it. Okay. So I just want to make some few comments before getting on to the mathematical part. So clearly there is a beauty and elegance to the proof. And where does this notions of proof, beauty, and elegance arise from? These are all really abstract mathematical topics, questions. So, of course, mathematics has a utilitarian aspect. It's used in many subjects and topics. But here we are doing mathematics in some sense for its own sake. And it acquires some kind of emotional overtones, or you can say artistic or whatever, artistic overtones, where you try to talk about beauty, about whether the proof is nice, whether the mathematics is good. There are very subjective tones, subjective judgments which are made by mathematics. Of course, these are questions which occurred to me also. This was some time back, but so thinking about this, Enrico and Guido, is mathematics hereditary? If so, when did mathematics, modern human beings, acquire the mathematical genes? And if you can go to a different subject and ask about that. You can ask about, easier to ask about music, which has no utilitarian role to play. And so you can ask whether, and it does neither gives us any material sustenance. Nor is it required in finding a mate, except in Indian films. It's also pretty interesting to see the depiction of music in Indian films from the 50s and 60s, when it was mostly separation and people singing alone, then romantic, and now it's groups of people dancing together. So, and none of the other mammals seem to have it, and only the small birds seem to have developed a musical consciousness, right? So why has music developed in humans? And when did it start? Before intelligence or after intelligence? I don't know. And you can add your own questions. And of course, more useless than music is philosophy, where one can even go to war on philosophical issues. But then the questions start looking more and more philosophical. So it's not clear whether mathematics is hereditary. Why does one want to do mathematics? Is there some beauty? Where does it come from? All these ideas. But okay, so let's start off get back to mathematics, the number theory, which I want to look at. So much of number theory can be motivated from the problem of finding out which right triangles are integer sides. So this was a question which was, many examples are known from the time of the Babylonians, okay, which is more than 4,000 years ago, and also found in the Sutras. Yeah, so the Pythagoras theorem is not really due to Pythagoras. It was there in the Babylonians. All ancient civilizations had it. And these examples are there in the Babylonian. It's around 60 examples of right angle triangles with integer sides. And these examples, 3 squared plus 4 squared is 5 squared. We all know that. We have seen it. 5 squared plus 12 squared is 13 squared. 165 is 144 plus 25, 169. 8 squared plus 15 squared is 17 squared. And so on. So there are all these kind of examples which we know of. And I also want to bring to your attention the last two examples, 6 squared plus 8 squared equal to 10 squared. Now this example has been got for the first by multiplying 3 by 2, 4 by 2, and 5 by 2. So it's just scaled up of this. And similarly, this last example is scaled up by 3 of the first example. 3 into 3 is 9, 4 into 3 is 12, and 5 into 3 is 15. So that's some property of homogeneity, which we'll use later in finding the Pythagorean triples. So that's what I'm going to come to next. We want to find a general formula for the Pythagorean triples, x, y, z, solutions to the equation x squared plus y squared equal to z squared. All right, integral solutions which you want to look at. Okay, so this is what I said, that the last two solutions differ from the first by multiplication by a factor of 2 and 3 respectively. The terms here. So if ABC is a solution, so if you have a solution a squared plus b squared equals to c squared, then you can multiply each of the entries by d, some integer d. D might be 2, 3, 4, 5, 10, anything, 100. and you get another solution because it will pull up, d squared will pull up, d squared pulls up, and d squared pulls up. So you have another solution of that. So that is what is called homogeneity in this thing. And this observation can be reversed. Okay, so I'll recall some basic aspects of number theory or arithmetic about what is called divisibility, which is taught in schools. So recall that a number d is a factor or divides the number a if a can be written as a equal to k times d, where for some integer k. That means d divides a, or d is a factor of a if a is equal to some multiple of d. Right? That's what it is. Okay. In other words, saying that it's a multiple of d, meaning if you divide a by d, it does not leave you any remainder. It's also an integer. It's a proper integer. Okay. In mathematical notation, this is written as d divides a, but I'm not going to use that notation, so it's okay. Okay. Then let me recall another concept coming from, again, it goes back to school days. A number greater than 1, whose only factors are 1 and itself, is called a prime number. So the examples of prime numbers is 2, that's only odd, and then 3, 5, 7, 11. And in some sense, as people say, 2 is an odd prime number because it's an odd man out. But anyway, but all the others are odds. And the distribution of primes and other things is fairly mysterious, and it's one of the major aspects of study in what is called analytical number theory. But the important fact that we want to use in today is that any natural number can be uniquely written as a product of prime numbers. Okay, so that one we have seen it. So if you take a number 18, so that's 2 into 3 into 3, right? You cannot break it up any further. 30 is 2 into 3 into 5. 57 is 3 into 19, and so on. So, and these factors are unique and up to rearrangement. You can also say it is 3 into 2 into 3 or 3 into 3 into 2, but up to rearrangement, these factors are all unique. Okay, so that is one of the first things which you want to use, that any natural number can be uniquely written as a product of prime numbers. Now let's get on to what are rules of divisibility, the greatest common divisor. Suppose d divides a and d divides b. Right? Oh, I am using the notation. Okay. So then it's easy to say that then d divides the sum a plus b. I'm not going to give a proof. It's fairly easy to see that. And d also divides the product ab. D divides the product ab. Okay, so these are easy, that if d is a factor of two numbers a and b, then d is also a factor of the sum a plus b, and b is also a factor of the product a times b. So what you can do is you can define, given two numbers a and b, the greatest common divisor GCD of a and b is the largest amongst the positive numbers d that divides both a and b. Okay, so that is called the greatest common divisor. So examples, if I take GCD of the two numbers 12 and 15, then clearly 3 is the largest number that divides both 12 and 15, and so 3 is the GCD. And if you take 16 and 24, then 8 divides both 16 and 24, but that is the largest. Anything else has to divide. And GCD of 50 and 75 is 25. Of course, the point about GCD is that it's not only the greatest, but any number which divides a and b will also divide the GCD. Yeah. So this is what is. So if d is the greatest common divisor of a and b, then dividing both a and b, they will have 1 as a common factor. And so what you have is that GCD of a by d and b by d equal to 1. Check, you can say GCD of 50 by 25, 75 by 25 is GCD of 2, 3, and there are no further common factors. So you removed all the common factors. A different way of putting this is that if I do the scaling, GCD of d times a, d times b, then d pulls up. D is GCD of a times b. Yeah. So all these statements and some other statements follows from expressing a number uniquely as a product of primes. So if you use that fact, then all these statements come out somewhat easily. There is also another notion which I want to say, from prime to co-prime. So you want to say two numbers are said to be co-prime if their only common factors are 1 and the number itself. Okay. So now if D divides two numbers in a Pythagorean triple ABC, right? So then D squared, suppose two numbers, say, suppose if it divides A and C, if D divides A and C, then we will have that the square B squared divides A squared and C squared. And so hence D squared divides C squared minus A squared equal to B squared. And it follows from what we have said from the uniqueness of prime factorization that D divides B. Okay, the various aspects. So what happens is, if D divides two terms, I've taken A and C for example, but you could have taken A and B or B and C or any of this. If you have a common factor for two of the terms in a Pythagorean triple, then it will divide the third term. Okay, so what this says is that we can dividing by the common divisor, say greatest common divisor, A and of say C and A or A and B, whatever it is. D is again or divide. So you also have a solution again. A by D whole square plus B by D square is equal to C by D square. Okay. So from whatever I've told you above, so we can divide by the greatest common divisor of say A and B, and then we can, or whatever it is. So hence it's enough to find those solutions A, B, C which have no common factors. Okay. So what I'm saying is that by dividing by GCD of any two of the numbers, they're all equal. So we can assume that the greatest common divisor of A and C, A, B, and BC are all one. In other words, these numbers A, B, C are mutually co-prime to each other. So we can do this because this equation is homogeneous of a very particular kind. There are no coefficients also. Okay. So such solutions will be called primitive solutions, and I'm going to give and first find out what are all the primitive solutions. Okay, so we are considering solutions A squared plus B squared equal to C squared, such that the terms A, B, C have no common, non-trivial common factors with each other. Okay, in particular, both A and B cannot be even, right? Because if A is even and B is even, so 2 divides them, and that cannot be possible. So we can assume that, for instance, but I'm going to claim that both A and B cannot be simultaneously odd. So this is a very key part of the argument. That's why I've outlined it in red. To say that A and B cannot be even is easy because 2 divides that, and we have assumed they are co-prime. But to say that A and B cannot be simultaneously odd is slightly more work, and we'll see why it's true. So if A is odd, so the proof comes by looking at remainders modulo 4. Okay, so I'll tell you what is the reasoning. So if A is odd, then it is of the form A equal to 2k plus 1 for some number k. So you square. So the square of A is 2k plus 1 whole squared, which is 4k squared plus 4k plus 1. So what you see is that this A squared leaves a remainder 1 upon dividing by 4, right? That's what it is. Similarly, B squared also leaves a remainder 1 upon dividing by 4. So if B is odd, if A and B are both odd, A squared will leave a remainder upon 1 upon dividing by 4. B squared leaves a remainder 1 upon dividing by 4. The sum leaves a remainder 2 upon dividing by 4, right? Which means C has to be even. 2 has to divide C squared. But if C is even, its square is to be divisible by 4. It can't leave a remainder 2 upon dividing by 4. So that is the contradiction why A and B are this. So the sum, so I'm just written it down. Similarly, B squared leaves a remainder 1 upon dividing by 4. The sum A squared plus B squared leaves remainder 2 upon dividing by 4. But C is even. So C squared is divisible by 4. That leads to a contradiction. Right? So both A and B cannot be simultaneously odd. Okay. So this example, the foregoing example, is an example of a local argument based on the prime 2. So when I said in the title, the local global principle, so this is the beginning of the local arguments. It's based on the prime 2. Okay. So now assume now, but we want to go back to the solution of the Pythagorean thing, where for solutions of the primitive Pythagorean triples, we now assume A is even and B is odd. So then, of course, C is also odd. C can't be even, of course. Only one number can be even at the maximum, right? So we write the equation now, we rewrite it. A squared, so the even part is kept here, and I take the two odd parts, c squared minus b squared, and I factor it as c plus b into c minus b. Okay, since both b and c are both odd, so the sum are even. C plus b and c minus b are even, which means c plus b and c minus b are divisible by 2. Right? So now the next key observation is that I take the greatest common divisor of c plus b by 2, because c plus b is even, I can divide by 2, and c minus b is also even, I can divide by 2, and it is equal to 1. That is, they have no common non-trivial factors, right? So that is it. So what is the proof? If d divides, it's pretty easy. If d divides c plus b by 2 and c minus b by 2, then d divides the sum, which is c, because the b by 2 cancels, and d divides the difference, which is b. So, but we have assumed that the greatest common divisor of b and c is 1. There are no common non-trivial common factors apart from 1, which means that d divides both b and c, so which means d has to be equal to 1. And it follows that the greatest common divisor of these two numbers is 1. Okay, so that's good. So now I write a is, so recall that a is even. A is, so I can write it as 2 times a dash. So a squared is 4 times a dash squared equal to c plus b into c minus b, right? So I divide by 4 and I distribute the 2 into both c plus b and c minus b. So a dash squared equal to c plus b by 2 into c minus b by 2. So recall, so what we have is that there are this c plus b by 2 times c minus b by 2 is square, and these are two co-prime numbers. G plus the greatest common divisor of c plus b by 2 and c minus b by 2. So now the next key observation, which comes from the uniqueness of prime factorization, if you have if you have product of two co-prime numbers without a common factor is a square, then each one of them is a square. So that means c plus b by 2 is a square and c minus b by 2 is a square. Okay, so this is, again, one can see that. So you write c plus b by 2 equal to m squared, c minus b by 2 equal to m squared. So we are almost done, except for one more observation. So what are the possible? Then c is equal to m squared plus n squared, and b is equal to m squared minus n squared, and a is equal to 2 times mn, right? Because a is equal to 2 times a dash, and a dash is m times n. Okay. Yeah, a dash squared is, so that is, except we want to make one slight observation about m and n. Any common factor of m and n will be a common factor of b and c, or whatever it is. So hence m and n can have no common factors, because we assume b and c do not have, or a do not have any common factors. Okay, so that is one of the first conditions. The second condition is both m and n cannot be simultaneously odd. If they are simultaneously odd, then all of them will be even. C is even, B is even, and A is even. But we have ruled that out. Okay. So contradicting our hypothesis. Okay, so we have proved the following theorem. So this is what we wanted to see. So that's it. We have got the theorem, all Pythagorean triples, the solutions to the Pythagoras equation, x squared plus y squared equal to z squared, with GCD of xy equal to, with a coprime. Any one of these conditions consists of numbers of the form, say up to, x may be, if I'm assuming x is even, then it is 2mn, y is m squared minus n squared, and z is m squared plus n squared. So I said only, all three cannot be odd, only one of them will be even, and I will assume that x is even, right? And so then it will be 2 times mn. These are all the solutions. These are the primitive solutions. And any non-primitive solutions, and where m and n are co-prime numbers, and both of them cannot be simultaneously odd. So now you just plug back m equal to 1, n equal to 1, and so on. You will get all those equations, all the solutions which you can get. The general solution is obtained by scaling. So you scale this solution by some number d. So d. So by homogeneity, these are all the general solutions, where d is any integer. Okay, so that is the first step. I wanted to come to the solution of the Pythagorean thing. And if you have found this, if you understood this, that would be really nice. Yeah, if anybody wants to ask any questions, feel free to do that. So you can check this out. Okay, otherwise, let me go ahead. So having tasted success, then of course, mathematicians are clever at causing problems or posing problems. So now we want to pose problems to ourselves. We now consider solving other equations. So for instance, can you slightly look at equations like x squared plus 2y squared equal to z squared, or 3x squared minus 5y squared equal to 7z squared. Can you solve these equations? Okay. Of course, you cannot really factorize or do the kind of reasoning which you have worked so far with the Pythagoras. It's slightly tough. You cannot really factorize it. Say 7z squared plus 5y squared, you cannot really factorize it. Okay, of course, here z squared minus x squared you can factor, but this equation you cannot factor. Even if you manage to factor them, we cannot argue as before about the GCDs and that each factor is a square and so on. It all came out because of a very particular solution to the form of the Pythagorean equation. Okay, so that's there. And of course, you would say, oh, mathematicians are crazy enough. Why do you want, they consider all such questions, artificial questions and whatnot. But why do you really want to consider such questions? So there's a good reason why mathematicians landed on such questions. And that goes back to a discovery of Fermat, which I want to talk about. So Fermat made the astounding discovery, again, probably partially motivated by the Pythagorean theorem. So he wanted to raise the question of which numbers are of the form the sum of two squares. So that is a question which Fermat said, and he made the astounding discovery of the following. An odd prime p can be written as a sum of two squares, p equal to x squared plus y squared, precisely when p leaves the remainder. Of course, p can be 2, that is not an odd prime, 2 is 1 squared plus 1 squared, but if I'm looking at odd primes, p leaves the remainder 1 upon dividing by 4. Okay, so let's look at some examples. If I say 5, 5 is an odd prime, it leaves, sorry, remainder 1 upon dividing by 4. So I can write it as 2 squared plus 1. 13 is 3 squared plus 2 squared. 41 is 5 squared plus 4 squared. 73 is 8 squared plus 3 squared, and so on. Okay. Now, local reasoning, meaning considering remainders upon dividing by 4, because you have sum of two squares. So that will, if you take the remainders upon dividing by 4, will imply that sum of two squares will have only remainders 0, 1, or 2 upon dividing by 4. But so you can never get that a prime p which leaves a remainder 3 upon dividing by 4 cannot be written as a sum of two squares. Okay. So the really amazing part is that any prime which leaves, the solution is extremely simple for the Fermat theorem. Now, if you are given a prime, like say 73, right? It leaves a remainder 1 upon dividing by 4. That's a very simple calculation. If you know it's a prime, and it's a very simple calculation. But once that fact is given to you, then you can be rest assured that you can write it as a sum of two squares. So this is a quadratic nonlinear problem about primes. And as I said, primes are fairly unpredictable. It's not easy to figure out a pattern to generate the next prime number, the nth prime number. You can only talk about its size and things like that. But it has an amazingly simple solution. This was a gold mine. Fermat really fully recognizing the great discovery that he had made, followed it with other examples. So if you look at p odd and you want to write a prime p as a sum of x squared plus 2 twice the square, then this happens precisely when p leaves the remainder 1 or 3 upon dividing by 8, right? If I take, just look at this. And similarly, if p is not equal to 3 and p can be written on the form x squared plus 3y squared, precisely when p leaves the remainder 1 upon dividing by 3. Okay, in case you think that these examples can be generalize to x squared plus 5y squared x squared plus 7y squared and all, then you'll be mistaken. It gets really complicated. But let's look at some examples. It's fun. Take 19, it leaves the remainder 3 upon dividing by 8. I can write it as 1 squared plus 2 times 3 squared. 43, it leaves 3 upon dividing by 8 is 3 squared plus 2 times 4 squared. 73, which leaves the remainder 1 upon dividing by 8, which is 1 squared plus 2 into 36. Similarly, for the second example, again, we can write 13 as 1 squared plus 3 times 2 squared. 43 is. So you can just check. See, 73 falls, both 13 and 43 and 73 falls into both the examples, and they can be written in this different way. So the solution is amazingly easy, and it's really an amazing thing. 100 years later, so Euler came across this above claims of Fermat when he was around 20 or something. And Euler had luckily a long life, and he began a lifelong quest for the next 60 years or so to understand this phenomenon. And towards the end of his life, Euler, and then it was followed by Legendre, who formulated what this things are called, what are called general solutions to quadratic equations, and eventually more general equations. These are called the reciprocity and the proof. Okay, but cutting short a long history, the proof of Fermat's problem, the equation x power n plus y power n equal to z power n, that is, if I generalize the Pythagorean beyond exponent 2, n is greater than or equal to 3, then you have only the trivial solutions. There are no non-trivial solutions. One of, by trivial meaning either x or y equal to 0 and x equal to plus minus z or something, right, at the maximum. Has no non-trivial solution by Wiles and Taylor-Wiles, is to essentially prove a grand generalization of this phenomenon called as reciprocity loss. Okay, and I just want to say that the entire program rests on harmony. We're coming back to some kind of music, of which Ramanujan was one of the earliest discoverers of harmony in mathematics. Okay, so that's back to some mathematics now. That was a bit of history, but I just wanted to tell you about the reciprocity laws, which is, I thought, was one of the really most amazing aspects of mathematics and number theory, which is one of the central aspects of number theory. So back to our problem of solving quadratic equations. So what we are going to outline now is a geometric method, the method of stereographic projection, which one knows from the theory of map making, that allows us to solve these equations, but at a slight cost. Okay, at the cost of solving it in rational numbers rather than integers. Okay, so for the sake of drawing pictures, so one can do it even with x, y, z, but let me do it with rational numbers. Anyway, so we divide by z squared, say by z squared, and rewrite the equations in two variables. So previously I was looking at x squared plus 2y squared equal to z squared. I make basically z equal to 1. I look at x squared plus 2y squared equal to 1, or 3x squared minus 5y squared equal to 7. These forms ellipses or hyperbolas in the plane, or even a parabola, whatever. Right? Now we ask for solutions A, B, where A and B are rational numbers, that is of the form R by S, where R and S are integers and S is not equal to 0. Okay, that's the kind of solutions. Okay, so A squared plus 2y squared equal to 1. So now I want to recall a few definitions so that it makes it easier. This entire method is a purely thought process. You don't need to actually do any calculation, provided you know some basic facts. So again, these are all goes back to school mathematics. A point A comma B in the plane with x coordinate A and y coordinate B is said to be rational point if both A and B are rational numbers. Okay, similarly, if you take a straight line, it's said to be rational if it has an equation of the form, the straight lines are linear equations, ax plus by equal to c, where a, b, and c, you have guessed it, will be all rational numbers. Okay. Similarly, a conic section, by which one means a circle, ellipse, hyperbola, pairs of lines, or whatever it is said to be rational. A conic section is defined by a quadratic equation, ax squared plus bxy plus cy squared plus whatever something, if all the coefficients a, b, c, d, e, f all are rational numbers. If it can be defined by a quadratic equation which are rational. Of course, it can be defined by only one equation up to scaling. So all we are saying up to scaling, all the equations are rational numbers. Okay. So what is the method of stereographic projection? So you are going to project from a point Q, and the point is, so suppose this is the ellipse or hyperbola or whatever it is, it's a conic section, and you're going to project it to another line which is called EP, the line E or EP dash. Okay, the line E. So you have this conic Q, you're projecting from Q. So what you do, you take Q, join it to a point P, extend it, and wherever P dash hits it, that's where P is sent to P dash. Okay. Conversely, if you have a point P dash on this line, you can join that to Q, and wherever that cuts it, that's the point P. So what I'm going to show is that basically this gives you a one-to-one correspondence between points on this line. That is, if I'm having, it hits uniquely at this point. And similarly, if I have a point out here, I get back a point here, right? Except the point at infinity, which will be tangential to this. So in this way, I'll be getting a correspondence between points on this line and points on this circle. Okay, so this is pure thought. There is nothing really, there is of course some slight mathematics which we'll come to know, but that is all there is to it, right? And but what we are going to say is that using this stereographic projection, we can find all rational solutions. The way of doing it is a purely algebraic way of doing it, which is what we are going to say. We will now see that stereographic projection preserves rational points. What does it mean? It means stereographic projection from a rational point. If Q is a rational point lying on a rational conic to a rational line, then it sends rational points on the conic to rational points on the line. So basically, let me go back to this example. If this conic is rational, if this equation is rational, if the straight line is rational, then stereographic projection, and if Q is a rational point, it will send a rational point P to a rational point P dash, and vice versa. If P dash is a rational point, then this point P is rational. So it gives you a bijection or a one-to-one correspondence between rational points out here and the rational points here. So that is all that stereographic projection does. And so it allows us to find all rational points on the conic or line in terms of rational points on the straight line, which is much easier to find, right? So the geometric method is based on the following principles. Let me restate the following. The line joining any two distinct rational points is a rational straight line. Okay, so if you have two distinct rational points on the plane and distinct, then the line joining them is a rational straight line. Any two non-parallel rational lines meet at a rational point. If you have two equations, linear equations, which you have all seen, A1, B1, C1, and A2, B2, C2, if they are all rationals, all the equations, then the solution, if it is non-parallel, it's a unique solution, that's also a rational point. And now the third is, there's a slight bit of reasoning. If a quadratic equation ax squared plus bx plus c equal to 0 with coefficients a, b, c are rational numbers, and if one of the roots is rational, then the other root is also rational. Okay, a quadratic equation has generally two roots, and if one root is rational, in a rational quadratic equation, then the other root is also rational. And the fourth is, of course, a straight line meets a conic section, circle, ellipse, or whatever at most 2 points, because one is a quadratic equation, other is a straight line. So the proof of one, if I have x1 and y1 and x2 and y2, and a general point xy, so we look at how do you construct the slope, the straight equation of the straight line. The slopes have to be equal. The slopes are all equal. So what you get is the slope y minus y1, that is this distance upon the horizontal distance, by x minus x1 is equal to y2 minus y1, this slope, y2 minus y1, by x2 minus x1. So the slopes are equal because they are similar triangles. And so you write, you get y equal to y1 plus x minus x1 equal to y2 minus y1 by x2 minus x1. Recall that y2, y1, x2, x1 are all rational numbers, and x2 is assuming x2 is not equal to x1. So then this is a non-zero rational number. X1 is rational, y1 is rational. So this is a straight line with rational equation with rational coordinates. So it's a rational straight line. Okay. So that is the thing. So if you take an example 1, 2, 3, 4, then you can check that y is 2 plus x minus 1, y is equal to x plus 1. So that's a straight line, which passes through these 2 points. And it's a okay. Proof of 2 is, as I said, is even easier. Given the equation of one straight line, you just substitute, can solve for y. Y is equal to c1 minus a1x upon b1, and then you substitute it in the other equation, and then you get that. It gives a rational solution equation in x, and so the x coordinate is rational. From this, the y coordinate is also rational. This is fairly easy. I'm going to skip this and go ahead. Okay, so you can see this solution. Now let's come to the fact 3 roots of a quadratic equation. If I look at ax squared plus bx plus c, then it is equal to a times x squared plus x times b upon a plus c upon a, right? And that I can write it as a into x minus alpha plus into x minus beta. Okay. So this satisfies upon comparing equations. The quotient of b is minus a into alpha plus beta. A is rational, b is rational. If one of the roots is rational, then alpha plus beta is a rational number. So then beta is also rational. Okay. So that is fairly easy to see. So that gives you this proof. So now what you have seen is stereographic projection for the point Q. So let us now see what is happening. I have Q is a rational point. Now this line, suppose P is a rational point. The line joining QP is a rational straight line. And I've taken another rational line. P. This is a rational line. So if this is a rational straight line, it will meet this another rational straight line at a rational point P dash. Okay, so given a rational point out here, I get a rational point P dash on the straight line. Conversely, if I have a rational point P dash, that will meet this, take the line joining P dash and Q, that is going to be a rational straight line. Now it will meet this conic at 2 points. One is Q and the other is P. But we know Q is rational, the coordinates. So which means also from whatever you have said that P will also be rational. Okay, so that is all there is to it. And so let P be another rational point on C. So this is what is the reasoning. The line QP is a rational point by principle 1. Suppose there is another rational point on the line, right? On the rational line on the plane called the line E, right? The intersection of the line QP and E is again a rational point P dash, right? Conversely, given a rational point P dash on E, the line joining Q and P dash is a rational line. Its intersection with the conic has 2 points of intersection. Since one of the points Q is rational, it follows from principle 3, slight bit of work, that the other point is also, P is also rational. Summing up, we have proved the following theorem. Okay, if there is a rational point and a rational conic, we have started with a rational point Q, then the collection of rational points in the conic can be parameterized by the rational points on a straight line. Okay. Or by the rational lines passing through the rational point. It's the same. We have worked with rational lines passing through the point Q. Okay, in particular, once there is one rational point on the conic, what you get is there are infinitely many rational solutions to the conic, because there are infinitely many rational lines through Q, or there are infinitely many rational points on a rational straight line. So see, it's an amazing thing. Once you have one point, you are able to get an infinitely many rational points. Okay. So rational parameterization for the circle. So let's do this, consider the equation of the circle. I'm going to go through this a bit fast. You can work it out slowly at home, but let me say, so x squared plus y squared equal to 1. So I'm taking this. So I have to start with the rational point. The point I'm going to start off with is the point Q is minus 1, 0. And that is for a particular reason. And the rational line to which I'm projecting the stereographic projection is this y-axis, right? So this is where I'm going to project. That's a rational straight line. And I'm taking from this point and I'm going to project points on the circle to this line. Right? So suppose if I have an equation, so this is the point on the circle x, y, that meets this point at a height t from the origin, from this x-axis. So the coordinate is 0, t. And I would like to know what are x, y in terms of t or other way around, right? So take, for instance, the point Q is -1, 0, and the line E to be the y-axis. The line joining -1, 0 on the point xy on the circle. So I have to find out what this point is, right? Meets the y-axis at the point 0, t. So we'll have to find out what is the equation of the straight line. Here, t is the slope of this line, right? T is the slope because this is the height and this distance is 1. So t is the slope of the straight line. Okay. So the equation of the straight line, we can check, is y equal to t times x plus 1 is tx plus t, right? When x equal to -1, this becomes -1 plus 1 is 0. So y is 0. And when x equal to 0, that is, then it is equal to t, right? So this is it. So now you substitute the equation of the line and the equation of the circle, and then you solve. It can be rewritten x squared plus t squared times x plus 1 whole squared equal to 1, because this is y equal to t into x plus 1. So now you gather together, it's 1 plus t squared into x squared plus 2t squared x plus t squared minus 1 equal to 0. Now, one of the roots is x equal to -1. We know that the sum of the roots is minus this negative second quotient, right? Divided upon this leading quotient. So one of the roots is -1. The other root is x. So x plus -1, x minus 1 is minus 2t squared upon t squared plus 1. So what you get is x equal to 1 minus t squared by 1 plus t squared. And then you get y, if you substitute t into x plus 1. So then you get is equal to 2t by 1 plus t squared. And then z will be, so that is x and y, and z will be, z is 1, z squared is 1. So these are the solutions. So these are the points. X is 1 minus t squared by 1 plus t squared. Y is 2t by 1 plus t squared. This is t. But what is, if I think xy, this is a straight line parameterizing. From origin, if I take the line, then x I can write it as also cos theta, sin theta. This is called a rational parameterization, because these functions are rational functions of t, polynomial divided by another polynomial. So if you substitute rational solution values for t, then you get rational values for x and y, right? So that is why it's a polynomial solution. So in this way, you get all the rational points on the circle. Okay. The usual trigonometric parameterization of the circle is I write x as cos theta, y as sin theta, where theta is a line joining, angle formed by the line joining origin and the point p equal to xy of the x with the x-axis, right? And what is t? And the point 0t with the x-axis. So t is tan theta by 2. Because if theta, so if I want to say this, so let's get back to the circle. So this is the angle theta, and this angle is theta by 2, right? Because this is the exterior angle, and if I form this is theta is the exterior angle, so that is the sum of whatever. So this is theta by 2. So what you get is that t is tan theta by 2, and so you get the formula that x equal to sin theta is 1 minus t squared by 1 plus t squared is 1 minus tan squared theta by 2 by 1 plus tan squared theta by 2, and y is cos theta is 2 tan theta by 2 by 1 plus tan squared theta by 2. So this formula has the advantage that any trigonometric expression involving the sine and the cos can be expressed as a rational function in the variable t using the above substitutions. And thus can be easily integrated. Okay, so now we have taken a long time. We come to the main point. The rational parameterization method allows one to find all the solutions of a rational conic, provided we can find one rational solution to begin with. So the question is, when does there exist a rational solution? So the solution to this problem by Legendre introduces a fundamental principle in number theory. Okay, so what you do is I illustrate it by saying one example. We go back to considering now the homogeneous equation in 3 variables rather than the inhomogeneous conics we used to do the rational parameterization. There are some, but not too much differences, but we'll work because we can work with integral solutions and divisibility rather than rational numbers. That also can be done, but it's more complicated. The key idea is, as we argued before, about the remainders of squares upon dividing modulo 4. So we are going to use the same thing, but now we'll look at remainders modulo all natural numbers. So this is a picture of Rajan, whatever. This. So now consider the equation. So to illustrate the principle, I want to show you one thing. X squared plus y squared equal to 3 squared, and we want to find integral solutions. In fact, we claim there does not exist any non-trivial solutions to this equation. Of course, because homogeneous 0, 0, 0 is always a solution to take secant y equal to 0. So suppose you start with the small equation, smallest solution in some sense. If both x and y are divisible by 3, then the left-hand side is divisible by 9. X squared plus y. X squared is divisible by 9, y squared is divisible by 9. Which means this 3z squared is divisible by 9. So you have only a factor of 3. That means z squared is divisible by 3, and which means z is divisible by 3. So consequently, 3 should divide z. We can then cancel these factors from and then left with a smaller solution, and we can argue there, and we cannot keep dividing by 3 all again and again. So you will come to a stage when both x and y are not divisible by 3. Right? So we can assume that either x or y is not divisible by 3. But now you look at remainders. Write the number as 3 times k plus a remainder r, where k is a quotient and the remainder r can take the values 0, 1 or 2. So which means the square of a square, right, is 9k squared plus 6k plus r squared. So if I take the remainder upon dividing by 3, so we'll leave the remainder either 0 upon dividing by 3, if r equal to 0, or it will leave the remainder 1 if r equal to 1 or 2. So I'm taking remainders dividing by 3. Right? But the left hand side will either leave a remainder 1 or 2 modulo 3, because both of them are not divisible by 3. So either it's 1 or 2. But the right hand side is divisible by 3. So this cannot happen. See, x squared leaves a remainder 1. Y squared can leave a remainder either 0 or 1. This y squared can leave a remainder either 0 or 1. Both of them can't be divisible by 3. So it has to leave a remainder either 1 or 2 mod 3. So which means, but this side leaves a remainder 0 mod 3. So there is no equation. Hence, there cannot be any non-trivial integral solution to the equation x squared plus y squared equals 3. Okay, so I just want you to remind about what is called the usual arithmetic. We can add and multiply numbers. So fixing one integer, we can add and multiply remainders upon dividing m in a consistent manner. Take for example m equal to 14. Here 17 and 3 leaves the same remainder modulo 14. Similarly 6 and 20 leaves the same remainder modulo 14. And then 17 plus 20 equal to 37 is modulo 14 is the same as the remainder left by 3 and 6, which is the remainders, is 9. So 37 divided by 14 is 9 mod 14. It leaves the remainder 9. Similarly, you can multiply 17 times 20 is 340. That leaves the remainder 4, which is the same as 3 into 6 equal to 18 modulo 4. So what you can do is, when you're doing these remainders, you can add and multiply remainders and in a consistent manner. So that is what it means. So given the collection of remainders modulo m, they can be added and multiplied as we do for normal addition and multiplication of numbers. And this collection of numbers, the remainders modulo m, will be denoted by z mod z. I can add and multiply. So that is what is called a ring in mathematics. A primordial ring is usually the ring denoted by z, the rank of integers. And two numbers a and b are said to be equal modulo m if they leave the same remainder modulo m. M divides a minus b. If a and b leaves the same remainder modulo m, or m divides m. Okay. Now, this local, suppose you are given an equation over the integers, say 6x plus x to the power 4, a polynomial equation, plus 3y cubed z minus 20z equal to 0. Suppose there is a solution. You can check whether x equal to 2, y equal to 2, and z equal to minus 24 is a solution of this. Once there is a solution over the integers, this solution being exact, it does not leave any remainders modulo m. So it is also an exact solution modulo any dividing upon by any integer m. So you have a necessary condition for integral solutions to polynomial equations, right? And that is, for any m, there has to be integers which when substituted in the equation should give 0 remainder modulo m. This is a necessary condition. If there is an integral solution, then there is also a solution in the remainder arithmetic modulo any integer m. This is a necessary condition. So what is meant by local global principle is suppose if all these conditions are satisfied for every integer m, right? Then this is what we did for m modulo 3 in this equation, right? That is because we saw that this necessary condition is not satisfied, there cannot be any integral solutions. The local global question is whether these necessary conditions are sufficient. That is what is the main thing. Studying these solutions in this manner is called the local global principle. So I'll have to explain why it's called local. I'll come to that right now, but it's this. So let's now state the theorem of Legendre, which started this. So now you consider an equation of the form ax squared plus by squared equal plus cz squared equal to 0. So now I'm going to take a kind of general quadratic equation, but I'm assuming in some sense I've left out the diagonal factors for simplicity. We can handle that also. Okay. But if all a, b, and c do not have the same sign, suppose if all a, b, and c are positive, then this has only the trivial solution, because each one of them all the squares are positive, then only 0, 0, 0 is positive. So we'll assume that the numbers all a, b, and c do not have the same sign. Okay, and hence so that's what it is. So we'll assume now that a, b, and c do not have the same sign. If they are all positive or negative, then you can never have solutions apart from the trivial 0, 0, 0 solution. So we give different versions of Legendre's theorem. Okay, version 1, this equation has non-trivial solutions in integers if and only for each m we can find numbers x, y, z, not all of them divisible by m, but such that ax squared plus by squared plus c squared is a multiple of m. Of course, I can always take, if I take m, then that is a solution. That is a trivial solution. So what we want is a non-trivial solution in the ring of remainders modulo m for every integer m. Okay, that what Legendre's theorem is saying is if the necessary condition is satisfied, then it is also sufficient to solve quadratic equations, provided a, b, and c do not have the same sign. Version 2, I don't work with all m. I work with only prime powers. Okay, the equation, this thing, if and only if it has a non-trivial solution in the integers z mod prime power, m is prime powers, remainders mod prime powers if it is there. So when I work with a remainder mod prime powers, it is called local. Okay, when it is local at p. When I look at the solutions over integers, it is called global. So it is called, this is why it is called the local global principle. Okay. And version 3, Legendre's formulation is explicit and nice. I am giving a modified version of Legendre. It's finite. You can check it out for this. What Legendre says is, assume further ABC are square-free integers, okay, which you can reduce it to that case. So there are no squares in A, B, and C. Okay. To know whether the solution, it is enough to check it for M. You take M is a prime P, where only those primes P dividing A, B, and C are involved. You look at only those primes P dividing A, B, and C, provided at least 2 amongst X, Y, Z are not divisible. So you need only primes P dividing A, B, and C, and you check for non-trivial solutions. Okay. Because if one of them, if you, right? So once P divides one of the quotients, then you're left with only an equation like AX squared equal plus CZ squared equal to 0. P divides B. And you'll have to check for AX squared plus CZ squared equal to 0 mod P has a non-trivial solution. That is it. So for the prime 2, of course, there's a slight thing. You'll have to check with remainders up to 2 cubed equal to 8. Before talking about the equivalence of various versions, let me just consider the idea underlying the proof of Legendre's theorem. It's a very simple idea. So let me just state that. It rests on an identity of Brahmagupta and diffactors.
Rajan, you will have to wind up.
Yeah, so is it 5 minutes? Is it okay?
Yeah. Just,
okay. So
just
let me
alert you.
Yeah, I know. I told I will be taking slightly more time, but
Yeah.
yeah. I thought 1.25 hours will be fine. But let me give you this idea of Legendre's theorem. It's a very simple idea. So the proof rests on this idea of Brahmagupta and Diophantus, which is if you take the product of a squared plus b squared, sum of two squares times sum of other two squares, is also can be written of sum of two squares. A product of numbers, each one of them can be written as sum of two squares, is also a sum of two squares. This was known to Diophantus and also the more general identity. But instead of, you can put a coefficient, x squared plus cy squared times u squared plus cy squared. You have an expression. It's again an expression of the same sign. Okay. There are variants of this. You can change signs, etc. In modern language, this says that the norm map is multiplicative. If you take, I introduce square roots, norm of x plus square root cy is defined by, you take the conjugate and you multiply and you get x squared minus cy squared. And that is supposed to be multiplicative. When c equal to 1, this is the thing. This is supposed to be a picture of Brahmagupta. Again, okay. So now let's get to a solution, an example. I just want to illustrate it with an example. Take this equation 7z squared equal to x squared plus 3y squared. Now, how do you prove that, that it satisfies the natural initial conditions? Then it should have a solution over integers. So we check the necessary conditions. When I go mod 7, okay, going mod 3, I need to check 7z squared equal to z squared because 7 leaves a remainder 1 upon 3. But z squared equal to x squared clearly has non-trivial solutions. You go mod 7. So this one is 0. So which means x squared equal to minus 3y squared. But minus 3 is the same as 4. So x squared equal to 4y squared. But 4 is equal to 2y squared. So again, it's some square equal to some other square. This also has non-trivial solutions. So the necessary conditions are satisfied. Okay. And then so we should expect that this equation 7z squared equal to x squared plus 3y squared should have actual rational solutions. Now, how will we find it? So the idea is to use a Brahmagupta identity. Okay. We start from the necessary condition that there is a non-trivial solution modulo 7. Okay. So what is a non-trivial solution? 7 is equal to 2 squared plus 3. That's a non-trivial solution. Okay. Right. Okay. This is, of course, this gives you a solution with putting z equal to 1 and x equal to 1 and y equal to 1. But, right. But let me just continue. So we multiply the equation 7z squared equal to x squared plus 3y squared. I've taken the wrong example by 7. Okay. And yeah, I should have taken. So the equation looks even more complicated. So I'll get 7z squared. I'll put the 7 here. 7z squared equal to 7x squared plus 21y squared. It looks complicated, but that's not the way. But I use Brahmagupta's identity. 7z whole squared is x squared plus 3y squared times 2 squared plus 3 is 2x minus 3y whole squared plus 3 into x plus 2y squared. So what you get, a new equation, which is of the form putting w equal to 7z, and this is u. So you get w squared equal to u squared plus 3v squared, which clearly has a non-trivial solution by putting v equal to 0 and w equal to u. Okay. But once you have a solution, since this equation was obtained by really rescaling the one by multiplying by 7 throughout, if this equation has a solution, then the old equation also has a solution. And if the old equation had a solution, this equation has a solution. This is essentially the proof of Legendre's theorem. It proceeds by induction of the size of the quotients, bringing them down to the case where the two quotients are equal. Okay, so now I just want to quickly go. I don't want to talk about the equivalences of the various versions. That is fairly interesting mathematics, but I just want to say what happens next, because I want to say what is the Clay price. So higher degrees. Okay, so for quadratic equations, this local global principle works. It all works fine. The local solutions, the necessity implies sufficiency. If there are no local abstraction, then you have a global solution. But what one knows that if you just go 1 degree higher, the general local global principle is false on the nose. 3x cubed plus 4y cubed plus 5z cubed. this is not an easy example to work out, is solvable modulo m for all m, but does not have a non-trivial solution in integers. Okay, that is one can check it out. However, it is expected that the local global principle is false only up to a finite error. Okay, the examples, the putative counter examples to the failure of local global principle, if you have such an equation or any other equation, has only a finite error. So this is a problem which has been resisting efforts since the days of Legendre. Even for cubic equations, it is one of the clay problems. In the sense, this is one of the most crucial ingredients into the solution to the clay problem, which is called the Birch-Uniter conjecture, I think. And solving this is really probably the most crucial part of the Birch-Uniter conjecture. That's in a very precise mathematical sense also, that in some other context, that if you know the finiteness of this local solution to the local global principle, that there are only finitely many possible errors, then you know that the rest of the Birch-Uniter conjecture follows. Okay, so the finiteness of the Tate-Shafarevich groups of elliptic curves is what is the part of the Birch-Uniter conjecture, but if you know that, that is crucial for the rest of the proof. Okay, so this is the finiteness of error in the local global principle in general. Though it has been maybe formulated for the last 50-60 years, there has really not been any significant progress in this finiteness. So I thank you. Yeah, so thanks. Yeah.
Thanks, Rajan. Thank you very much.
Yeah, sorry, I went over time, but I knew I would go over time. So I was.
No, here students may have to go to some other place. So
yeah, I know. Yeah, I kind of.
Okay, we'll invite questions. If anyone has any question, please ask. Any questions from anybody?
I don't have a question, but I want to make a comment. This is the nicest picture of Legendre that I've ever seen. Usually he looks like hell. But so you found a really nice one, I think.
Okay. But by the way, Legendre writes, Legendre? No, Lagrange. Lagrange writes very beautiful.
No, I mean, even Legendre is very beautiful.
Yeah, even Legendre is also very beautiful.
Professor, I have a question.
Yeah.
Yes, please ask.
In the figure of a I don't know how to pronounce, every point on the circle is fixed. Like there is a P point. If we want to another point, then we take the point on the other side of the circle, like that.
Right. You mean the stereographic projection? Wait, just a minute. Yeah. So what is the question?
If we have another point on that graph instead of P in left side, so we can find the P, like, is there any point M? So we can find the parameters of M on the line M dash.
Right, right. If I know this coordinates of P dash and you know the coordinate of Q, then you can find the point P. See, that's what I illustrated by that the standard circle x squared plus y squared equal to 1. You know, if you know the coordinates 0, t, then you know this x and y is 1 minus t squared upon 1 plus t squared and 2t squared upon 1 plus t squared. Okay, so all the things are very explicit. It's a very you can work it out explicitly provided you have one rational point to start with. Okay. Once you have one rational point, then the rest of the process is very easy. But the existence of the rational point is a much deeper arithmetical fact. And that is really, in a sense, the best solution is the local global theorem of Legendre.
Okay, Professor, thank you.
Yeah.
Anybody with any other question? Okay, you can also write to Professor Rajan. He will reply.
Yeah.
Yeah. So thank you, Rajan, once again.
Yeah. Thanks. I hope. Yeah. Anyway.